Sweet. Alright. Today we're on 7.3 talking about rotations. What were the 3 different types of transformations that we've talked about so far? Travis, give me one. Rotation. Okay. Ryan. Reflection. McKenna. Translation. Okay. There's another I word that we're looking for. They are all what, Austin? Isometries, which means what? Remember? Anybody, help us out. Seth? Okay, so basically it preserves size and shape is what we said in class, meaning it's the same, right? If you rotate it, the shape doesn't change, it just moves to a different place. Same with reflection, same with translation. Okay, we know what a rotation is, right? We talked about that 2 days ago. Okay, so today we're going to do rotations. Tomorrow we're going to do what? Anybody remember? Quiz. Quiz tomorrow. Okay, and then Friday we'll do translations. Okay, today, rotations. Now I'm not going to define rotation, but I am going to define center of rotation. One second. This is 7.3 rotations. Okay, first definition is center of rotation. And there's a lot of us that can probably take a pretty good guess as to what this is. What is this? What's the center of rotation? Nobody? Royal?
The point at which the shape rotates around?
Right, so it's the point which you rotate about. I use the word about because that's the word your book is going to use. You guys can think of that as like around, okay? It's what you're going to rotate around. Same idea. 110. Thanks. Actually, do 111. Put 1 in Miss Olson's mailbox. Thank you. Okay, so that's the point which you rotate about. The next definition we have is the angle of rotation. Which is how many degrees you rotate a figure. Now that probably also includes your direction, like clockwise, counterclockwise. Okay, so be aware of that. That's also going to include your direction. Okay, so your angle of rotation might be 30 degrees counterclockwise, or 90 degrees clockwise, or something like that. Okay. Now we already did an example the other day of what a rotation looks like, right? You guys remember that? 7.1, we did an example of that. So I'm not going to do an example of that one. The next thing we come to is our rotation theorem. Okay, just like yesterday with our reflection theorem, it just says a rotation is an isometry. Do you need to probably write that down? Probably not. If you want to, feel free to put that on your theorem sheet, but you don't have to. Okay? So if you don't want to put that on your theorem sheet, you do not have to. Okay, but that is what's next in your book. Okay, after that, we're flipping clear over to page 414. Okay, the main thing that you're going to have to do today on your assignment is you're going to have to be able to take a shape in a coordinate plane and rotate it. Okay? But they're going to ask you to do it without using a coordinate plane on your homework. Okay, so we're going to go over that. I'll show you guys how we're going to do that. Okay. Oh, I actually need my graph first. If you want graph paper to take notes on, use the middle stuff on that bottom shelf, please. Don't use our good graph paper for assignments. Use that, it's like manila colored. Use that for me if you would. Okay, so let's say we're going to go ahead and start out in, first of all, you guys remember your quadrant names? Which one's quadrant 1? The top right is actually quadrant 1, okay, because everything's positive here. Where's quadrant 2 at? Top left, and this is where it goes kind of backwards for us. So we have 1, 2, 3, 4. Okay, so it's kind of backwards, okay, but it's 1, 2, 3, 4. So let's go ahead and let's just do a triangle on this first one. Let's put a triangle over here in quadrant 2. Okay, we have some very important rules for us that are going to help us do this or figure out where we're rotating it. When you rotate it about the origin, okay, it has to be about the origin. We're going to have some special rules that work here. Now this is -4, 1, this is -1, 4, and this one over here is -6, 5. Okay. Rule number 1. Every 90 degrees, you switch quadrants. Okay, so every 90 degrees, you're going to switch quadrants. This is when you rotate it about what? The origin. Always the origin. This only works when you're rotating about the origin. Probably next week we'll talk about rotating around a different point. But today, everything's about the origin today. Okay, so every 90 degrees, you switch quadrants. Okay, rule number 2, and this one's a little bit more confusing. Every 90 degrees, you switch the absolute value or values of x and y. And then your last step, step 3, decide whether x and y are positive or negative based on what quadrant they are in. Okay, so I know that last one's kind of long. Okay, so first thing you need to do is you need to understand if you're going 90 degrees, you got to switch quadrants, right? Yep. Okay. Second thing you need to do is you need to find the absolute values of your x and y's and switch them every 90 degrees. And then the last thing you need to figure out, are my new x and y's going to be positive or negative? Okay. So what we're going to do here, let's go ahead, let's rotate this counterclockwise, because on Monday we rotated clockwise. So on today, let's rotate this counterclockwise. Okay. So here, step 1, if I'm going 90 degrees counterclockwise about the origin, okay, 90 degrees counterclockwise about the origin, this point is going to end up where now? In quadrant 3. Okay, because each quadrant's 90 degrees, right? And you can easily prove that just by looking at there. Those are all right angles all the way around. Okay, so each quadrant's 90 degrees. So this is going to end up down here. Okay, well, the absolute value of negative 4 is 4, and that's 1, right? I need to switch them. So now it's going to be a 1 and then a 4, right? Okay, but if I want it down here, is it going to be a negative 1 or a positive 1? It's going to be a negative 1 and a negative 4, because it has to be down here in this quadrant. Okay. Up here, also going to end up in quadrant 3, correct? Switch them, so I have a 5 and then a 6, positive or negative? On both of them? Yep. So I have a negative 5 and then a negative 6. Okay, and then the last one, going to end up in quadrant what? 3. It's going to be a 4 and then a 1. But to be down here in quadrant 3, they both have to be negative, right? So it's going to be 4 and then a 1. So it's negative 4, negative 1. And then we connect our points. And that would be a 90-degree rotation about the origin counterclockwise. Did everybody get all those rules down? Okay, if not, there's the bottom one there. Decide whether x and y are positive or negative based on what quadrant they are in. Yes, sir.
Can you go off of like quadrant 4, the x's are always positive and the y's are always negative?
Right. Yep. So his question is, in quadrant 4, well, to be in quadrant 4, you have to go right, correct? So that means my x's are all positive. My y's are all going to be negative. Over here, quadrant 3, they're both negative. Quadrant 2, my x's are negative, my y's are positive. Quadrant 1, both positive. Okay, let's do another one. This time I'm not going to do a triangle, we're going to do a quadrilateral here. Okay, let's put 1 point here, 1 point here, 1 point down here, and then the other point right here. Okay, so I negative 4, 1. I have 3, 2. I have negative 2, negative 7. And I have negative 5, negative 2. Okay. Lainey, which way you want to go with this? Let's do 180 degrees. Okay, so if I go 180 degrees, does it matter which way I go? No, because no matter what, I'm ending up in the same place, right? Okay, so let's go 180 degrees. It doesn't matter which direction. Okay, so if I'm going 180 degrees, this point, after 90 degrees, ends up here, right? And after 180, ends up in quadrant 3. Okay? After 90 degrees, I get 2 and then a 3. After 180, I get a 3 and then a 2. So it actually switches back. But over here, they're both negative, right? So I go negative 3, negative 2. Okay. This one is going to end up in which quadrant? 1, because 90 degrees brings me here. 180 brings me here. 2, 7, switches to 7, 2, and then back to 2, 7, right? Okay, so I have 2, 7. This one's going to end up in quadrant 1 also. Okay, 90 here, 90 there. So 5, 2, then it's a 2, 5, and then 5, 2. Both positive up there, right? Okay. Last one. This one's in quadrant 2. 90 brings me here. 180 brings me down to quadrant 4. It's 4, 1 now. Now it's 1, 4. Now it's 4, 1. So I go 4, negative 1. I'm going to move this. Okay, and then I can just connect. Why what? I do every 90 degrees though. So 90 degrees switched me to here, and so then it was a 1 and then a 4, and then 90 degrees again switched me back to a 4 and then a 1. And then since it's in quadrant 4, my y has to be negative. Good question. Then we just connect our points. Okay? Yeah, Austin.
Is there a way to check if you did it right?
Just go through that same process would be the best way to check. Okay, just remember every 90 degrees. I mean, you can always do it twice, right? So do it twice. Be like, okay, 90 degrees, or excuse me, we went 180. So that point needs to go 180. So it goes to that quadrant and then that one. 180, it goes 1, 4, and then 4, 1. That's going to be your best way to check it. There's not really an equation you can plug into. There isn't an equation that you can plug into to check it. Okay, Travis? You could. It's going to take you quite a while, though. The only thing the distance formula would do for you is just making sure that the segment lengths were the same. Okay. Any questions on that one? Okay, that's probably going to be your most challenging part of today's homework. Now the next thing we need to do, go ahead and get your theorem sheets out. We're going to use our theorem sheets today. We have a theorem called the double reflection theorem. Now we're actually going to have two theorems called the double reflection theorem. Not today though. We'll have another one, might be Friday? Oh, just one theorem today. Okay, our double reflection theorem. And this one's a little bit confusing, so pay close attention to the words as you write these down. If lines K and M intersect at a point P, then a reflection in K followed by a reflection in M is a rotation about P. If lines K and M intersect at a point P, then a reflection in K followed by a reflection in M is a rotation about P. Does everybody see how we have two reflections there? Double reflection. Okay, we're reflecting over M, and we're reflecting over, K first, and then M. When we all get that written down, we'll do a diagram and talk about that a little bit more. Everybody have that? Yes? Okay. All right, so the diagram that we have going on here, I have line K, and I have line M. And they intersect to form point P. Okay? And they're actually going to tell you that this here, that's X degrees. Okay? And then they give us a segment here. Segment AB. And they want us to reflect it over K. Which gives me A prime, B prime. Everybody agree with that? Right? And then they want me to reflect that same thing over M. Which gives me B double prime and A double prime. And that, if I do a double reflection, that is actually the same thing as just taking AB and rotating it around this point to X degrees. Maybe I want to put that in a better place. Okay. So are they always going to have to probably give you this to solve something? Yeah, or maybe they give you this, but then you know this is a linear pair and you can find this. Okay, but somehow you're going to have to be able to figure out what this is to be able to know the angle of rotation here. Okay, so if this right here was 30 degrees and I did a double reflection of AB, how far did I actually rotate it? 60, because this was 30. 2 times that would be 60 degrees. So that would be a 60-degree rotation about what point? P. I know that's visually very hard to see sometimes. Okay, it's going to be obvious when you come across a problem like this because you're going to have a diagram that looks almost identical to this. You're going to have 2 intersecting lines and they're going to show a double reflection here. Okay, so it's going to be obvious when you come across a problem where you need to use this. Alright, take a look at example 3. That's probably the best example they have there for us for that exact theorem. Okay, they took triangle RST and they did a double reflection over K and M to get R double prime, S double prime, T double prime. Okay, instead of doing a double reflection, Tamaya, they actually rotated it how far? 120 degrees. Good, because the angle that they gave us was 60, so she just doubled that to get 120. Questions on that, guys? I know that's kind of a confusing diagram. I know the words are very confusing. But again, if you come across a problem where you need to use that, the diagrams are going to look the same every single time. Okay. The very last thing we need to talk about is rotational symmetry. Okay. A figure has rotational symmetry if it can be mapped onto, thanks Braden, itself in 180 degrees or less. A figure has rotational symmetry if it can be mapped onto itself in 180 degrees or less. Okay, it's going to be hard for me to show you on my board right now because it's kind of messed up. Everything's stretched out. Okay, but let's take a look. I think a square was working earlier. Okay, if I take this square and I start rotating it, is it going to fall back on top of itself in 180 degrees or less? Yeah, it actually did it twice at 180 degrees, right? Once at 90 degrees and once at 180. So does a square have rotational symmetry? Yes, it does. Okay. Would an equilateral triangle? Yes. Would a regular pentagon? Yes. Anything regular is going to. Okay. Any regular figure is going to have rotational symmetry. Now, if you take a look there on example 4, so what we just talked about, does a regular octagon have rotational symmetry? Yes, because it's regular, right? Everything's the same. That means the interior angles, excuse me, the interior angles are all the same, and the segment lengths are all the same. So it has to. What about that parallelogram? How many degrees does it take? 180. In 180 degrees, it'll fall back on top of itself. And part C, that trapezoid. No, that trapezoid isn't going to work. Actually, no trapezoid that I can think of is going to work. Okay. Okay, I know it wasn't super long, but are there any questions with any of that stuff today? Again, pretty similar with what we're looking at for the rest of the week for lessons, because we already went through everything on Monday, right? All right. On page 416 is our assignment. I'm just going to pull it off a plan book here real quick. Okay, remember tomorrow we do have a quiz. Your hardest problems today are going to be 13 through 19. Okay, so take your time on those. Those are challenging problems. Look at those closely as you go through.